Good evening, everyone. My name is Madrina Chirija, and together with Tahise Eugene, we're going to take you through a project that is intended. That's generative attention-based mechanism for adaptive and personalized learning system. Well, this project, having looked through the domain, which is education that we mainly focused on, we realized that the elementary education is it's underdeveloped. Like they don't take so much concern on it to make sure they can engage personalized techniques that can help it improve on its education. So with this idea, we're trying to look at elementary education, and in specifically, we are looking at the math department to see that we come up with a system that can reshape the education and enable students to acquire their full potential. So this system that we envision will adjust the work based on the students' performance and preferences, and this will help the students learn from their mistakes. And on the next slide, we talk about the techniques that we are actually going to incorporate so that we can achieve the best of this system. Kindly move to the next slide. On this slide, we're going to use 4 techniques mainly. That's retrieval augmented fine-tuning, natural language understanding, natural language processing, and generative pre-trained transformers. Well, retrieval augmented fine-tuning is going to help in retrieving information from external databases so that it's incorporated, and this will improve on the performance. Then for natural language understanding and natural language processing, this is going to help to understand the human prompts that are provided, and so that it can provide human-like text that the student can understand. Then for generative pre-trained transformers, these ones are going to, the aim is to enable chat boxes to understand and provide meaningful information. And these ones can help to give explanations, provide explanations to the students and provide summaries to the students so they can understand what they're talking about. And but as we all know, when you're coming up with a system, there are challenges that you actually face. And some of the challenges that we think we might be able, that we think we might face as we are trying to work on this system are on the next slide as listed. Kindly move to the next slide. So on this slide, we're talking about the technical computational problems that we are likely to face. The first problem is imbalanced classes. Imbalanced classes happens when when some classes are more represented than others. So this one causes the model to get biased. And when it gets biased, it can provide feedback that is actually not correct because it might focus on the majority over the minority. Then the other problem that we might face is overfitting and underfitting. Overfitting is when it learns too much from the trained data and it fails to make reasonable patterns when it comes to other information. Then for underfitting is when it fails to actually it fails to understand patterns when it comes to data that is provided to it. Then the other computational problem we are likely to face is data drift and concept drift. Data drift and concept drift is mainly the changes in the data that happens. For example, maybe it's used to answering questions of a particular kind, and this time around the student provides a question that it wasn't trained about. So that's a new problem that is being introduced to the model. So that's another computational problem that is most likely to be faced. Then another problem is model interpretability. This is all about transparency of the model, whereby the user, for example, the teachers and the parents, because this system we envision it to be used by teachers and parents to actually find out how the child is progressing, their strengths, their weaknesses, and all that. So model interpretability will affect transparency. So in a way that the parents and teachers might fail to find out, okay, they might find difficult in understanding how the model actually makes its decisions and makes its recommendations for what the student should learn and all that. And then another computational problem that is likely to be faced is scalability issues. Scalability is where the system, okay, where you're trying to accommodate new users or coming in. So when the number is growing big, scalability issues might be a very big challenge. Then another issue will be a cold start problem. Cold start problem is where the model does not have enough information so that it can give you recommendations. Like if you're a new user, it doesn't have any history about what you've studied. It can't know if I should recommend this for you or not. So it finds it hard to recommend what to give you. Then real-time processing requirements could be another challenge where feedback is needed at that exact time. So this one might be a bit hard. So that, and this might, when this happens, it might affect the experience of the student. Then the other problem is few shot and zero shot learning challenges, whereby there is little information for the model to learn. And with this, it will affect how best the model can provide reasonable answers. And the last challenge could be ethics in autonomous decision making, where the decisions that the suggestions that the model makes to the student would possibly affect their life in the real world. Yes, and but with all these technical computational problems that we might face, with the techniques that we've chosen to follow, to use, we believe that they can solve them in one way or another. Yes, so the next slide, we're going to talk about how best we can solve this, the proposed solutions. So for the proposed solutions, remember we've looked at problems like imbalanced classes, we've looked at data and concept drift and all that. So the natural language, we shall begin with the natural language processing and natural language understanding. Well, these two, we know that these ones are supposed to help us understand the prompt and then provide information that is readable to a student and that is human-like. So these two can help in these ones will help in model interpretability. Yeah, so they will promote transparency, as someone will be able to understand what the person is actually talking about. They'll also help in data and concept drift. Remember, data and concept drift is all about the changing patterns. So when the model is able to understand the prompt, it will be able to master the patterns that are moving on and know what to recommend next. So that one helps in data and concept drift. Then when it comes to retrieval augmented fine tuning, remember this one is going to retrieve data from external databases. So when it retrieves, it's going to help in the few shot problem. In the few shot problem, remember I said it's where it's learning from limited data when there is little data to learn from. So when the retrieval augmented fine tuning technique is able to retrieve data from external database, it helps the model to have more data that the student, that it can fetch possible responses from. Then the GPTs, that's the generative pre-trained transformers, these ones will help in providing explanations. So it will improve on the model interpretability so that it's easy for the teachers and the parents to know how the recommendations are being provided. Yes, that's what I had for you. I'll hand over to my partner to take you through the next part. Thank you.
Good evening, everyone. My name is Eugene Twaise, and I'm going to be taking you through the dataset description. So in this particular project we're doing, which is a generative attention retrieval augmented generation for adaptive and personalized learning, we are using a dataset that consists of grade school or elementary school level math, which is containing word problems that are designed to evaluate and fine-tune models for mathematical reasoning and problem solving in terms of how the students will learn mathematics. So we have two types of sets. We have what we call the train sets and the test sets. So the train sets, we have around 7,000 examples, and the test sets, we have 1,300 examples. So in this train and test sets, there are two categories. So we have what we call the normal tests and train sets, whereby it consists of data of JSON files or JSON line files that are shown in the next slide. So the example entry we have here is the way the data set is formatted. So we can see that there is a question and answer key values. So we store the questions and we also store the answers to those questions. So in the train and test data sets, we have two types. We have the normal train and tests, whereby we have the question in a word problem format, and it also tries to solve those problems immediately, giving a word or a text conversational mode of answering. Then we have what we call Socratic files. So Socratic files, basically, what these do is we have a question, as you can see here. We have a normal question. However, when it is answering, it's going to give a internal representation of that. So it will ask itself questions. For example, if I say Natalie sold clips to A48 of her friends, and they're asking her maybe how much did she sell in May, it will first interpret the question on its own with some reasoning and then solve the question later. So using this data set, we were able to come up with a few visualizations which were used to conduct exploratory data analysis, which help us to see whether this data set is very well capable and to help in creating a more sustainable data set and train our model better. So the first visualization we're able to comprehend is a word cloud. So basically, a word cloud helps us to see the most used text and create a cloud whereby the larger the texts, the more important or the most common it is in most of the questions in our data sets. So we can see that in this visualization, the most common words are total, many, and number, as you can see here. So we have total, many, and number. So we can see that these three are the most common. So you may be wondering, what do these things help us in? So a word cloud basically helps us find the common words that suggest structured responses with a formalized solution format. So basically, if numeric values are dominating, so we are trying to train the dataset to lean towards direct numerical answers. Then if we have text values which are dominant, then you are going to train it to go towards detailed explanations. So this matters because we want to help standardize the formats for explanations which are going to be generated by our model, and also in terms of debugging inconsistent and redundant answer patterns. Then the next visualization we are going to have, the next visualization we have is a violin plot. So here in this case, the violin plot we have is going to determine the violin plot of the question length. So it's going to help us to determine how far the number of words are depending on the questions that are asked. So these violin plots help us to analyze the variability of the length of the words. Then another graph we have is a KDE, or what we call a kernel distribution entity plot of the question and answer length. So here we are going to determine the density of the question length in correspondence with the answer length, helping us to determine based on the number of words of each of these questions. Then the next visualization we have is a word cloud again, but this time of the questions. The previous one we had of the answers, now this one of the questions. Then the next visualization we have the distribution of the answer categories. So we are trying to gauge the answer range depending on the answers we have. For example, from this graph, we see most of the answers are ranging between 10 and 50. Then the lists are ranging between 50 to 100. Then the next visualization we have are the answer lengths by category, by question category. So depending on the answers, how each operation is going to determine the length of the answer to be given. So we see if it's an addition, the answers are not going to be as lengthy as if it's a division or subtraction question. Then the next visualization, the next two visualizations are the question and answer length trends. So we are going to determine the index, graphing them against the number of words. So the number of words of each data set or of each example in that data set is going to be graphed based on their number of words. Then the next visualization we have a distribution of the numeric answers. So this one you can see we are getting their frequency based on the numeric answer by the 1 to the power 8th. So by the 10 to the power 8th. So you can see that most of the questions lie between exactly 0 and around 0.01 to the power 8th. So most of our answers are not corresponding to 1 to the power 8th, but they're really small values. Then the next visualization is a pie chart showing the distribution of numeric answers. So this pie chart shows us the percentage of most of the answers. As you can see here, the largest are the 10 to 50, and the smallest are the answers that range from 0 to 10. Then the next visualization is a distribution of the question and answer lengths, where we can see that the questions around the mean are longer than the answers around the mean, depending on the number of words and the frequency of those words. Then the last visualization we have is a relationship between question length and answer length in terms of a scatter plot. So we are basing, depending on the scatter plots that we have, we are getting them against the question length against the answer length. So we can see it's a bit more linear, where it's stretching up, it's going more positively, whereby we can find a few outliers whereby most of the